So let's look at the conjugate points on the catenary mathematically. We have our function for our catenary here, y equals c cosh x plus b all upon c. Now you'll note here that I've got the catenary drawn out here, and it's sitting based at the origin, and it's based at the origin here. You can see that this function is going to be symmetric about the origin. So it means that if we were to pick a point here for our x, let's say we call it h, then we're going to have the same point minus h along here, and it's going to give us some value for the y value k and the y value for k here. So we could write this out here as the k point, which is the height, which is the y, is equal to the c cosh, and we could put in minus h plus b upon c, but that's going to give us the exact same height if we put in the plus h plus b upon c. So this is really just a statement of the fact that this is a symmetric function, and whenever we go along this plus x and minus x, we're going to get a height of k and a height of k. Okay, and this is the height k here. Now if we were to make this value of b equal to 0, then we can say it's going to be symmetric about the origin here. Now we could move it about to other positions, but to make it simple we can just work it with it round about the origin. So we could say the value of b is equal to 0. So therefore we can take this c down, and we could say k upon c, which in effect is just our y height, is equal to the cosh h upon c. So let's have a quick look at this function here in the graphical calculator, and we'll see how the value of c and b changes the shape of it. So we have our catenary here, y is equal to c cosh x plus b all upon c, and you can see that whenever we adjust the value of b, all it does is move the function left and right. So it means that we could position this at b is equal to 0, and we can adjust the value of c, and the c is going to adjust the position here that it crosses the y-axis, the height, and also it changes the shape of the function here as well. Okay, it makes it narrower or it makes it wider. So we can pick the value of b equaling 0, and it just means it sits at the origin, and it simplifies things out. So we're going to be left with this simple equation here, the k upon c equals cosh h upon c. Now we're going to do some substitutions in order to split this into two functions. So we're going to have let's say our x is equal to our h upon c, so we can replace this h upon c simply with the value of x. So if that's true, then we have to say therefore that h is equal to c times x. Now we already know that y is equal to k upon c. So by substitution, if y is equal to k upon c, and also the value from c is equal to h upon x, so it means that y is going to be k upon h all times x. So just check that out, and it's just a little bit of simple algebraic manipulation. Now also we've got the other equation here, which is y is equal to cosh x. So we've split this into two equations here. We've got y equals cosh x, and we've got another equation as y equals kh upon x. But notice kh is just in effect the y and the x coordinate of a point. So if we think about this here as a constant, we're just going to have y is equal to a constant times x. So that's just going to be the equation of a straight line. Now I've actually got both of those drawn out here. We've got our y is equal to cosh x, which is this one, and we've got our y is equal to kh upon x, which is this straight line here. Now this straight line here is going to make an angle alpha with the x-axis, and we're going to have three possibilities. We could have k upon h is equal to tan alpha, so that is the gradient of this line here is the gradient of the tangent at this point, so it crosses at only one point, so there's only one solution. The other option is k upon h is less than tan alpha. So if it's less than tan alpha, then we're going to have the line here that runs along at this angle here, and when it runs along at this angle here, it doesn't actually touch the curve, so there's no solution in that possibility. Now there's another possibility that k upon h is greater than tan alpha. So if it's greater than tan alpha, then this line here is going to run up like this, and it's going to cut at 2 possible points. So we're going to see that there's going to be 2 possible solutions. So that's what we've seen whenever we looked at it geometrically. We noticed that if you had 2 points, then we could hang the rope in such a manner that we get 2 different catenaries. So this is the 2 solutions. So let's go ahead and we'll have a look at these different solutions in the graphical calculator. So this is the y equals cos x curve here, and we've got the equation of our line here, which is our y is equal to k upon h all times x. So that's this line here, and we've got our angle alpha here, which is the small angle in here. Now at the moment we've actually got it so that k upon h is equal to tan alpha. So you can see here that it's passing through this curve at only 1 point, so there's only one solution. But we could have it such that the k upon h is going to be less than tan alpha, in which case we're going to have the line here which won't pass the curve at any point, so there'll be no solutions in that possibility. Now there's always the other possibility we go the other direction, and we can have our k upon h is greater than tan alpha, in which case we can cross the curve at 2 points, this point here and this point here. So that's going to give us our 2 solutions. So the 2 solutions that we've seen from the previous video are the black curve here and the green curve here. Now in the black curve here, we said that between A and B we don't pass through any conjugate points, so therefore this will have a stationary point and it will be either a maximum or a minimum. In the second case here we go from A to B, but we're going to pass through the conjugate points, either A double dash, which is not shown here, but that's A double dash, and B double dash, in which case those are within the AB, and we're going to have a stationary point, but it's neither going to be a maximum nor a minimum. So it's the first one here, the black one, that we're interested in. But we're still going to go and look at this, how to work out the position of these stationary points analytically. So let's go ahead and we'll do that now. So let's cover the analytic derivation of the conjugate points of a catenary. We have the catenary equation here, and we found out from the previous video that this is the method we're going to use in order to find the x coordinates of the conjugate points. So we're going to find partial y by partial c, partial y by partial b, and we're going to divide them, and those are going to be partial y by partial c by partial y divided by partial b, wherever the x value is equal to a. So we're going to have the first derivation here, so we're going to do partial y by partial c, so we're going to use a product rule here, so we're going to differentiate the c, which is a constant, that disappears, we're left with the cos x plus b upon c, and then we're going to differentiate the this section here and then multiply it by the c. So we differentiate this section here, it gives us minus x upon c upon c squared sin x plus b upon c times the c. And finally the next line here, the c cancels with the c and we're left with this line here. So then we differentiate the partial y with the partial b, and the equation here, so in effect the c just looks like a constant here, so we take that out, so we're going to have a c upon c sin x plus b upon c. So that cancels with that, and you're left with the sin x plus b, and that should be divided by, so I'll just put the line in here, so that's the division. X plus b all upon c. So then what we're going to do is, I can leave this as an exercise for you yourself, but if you divide these out, so you're going to get a partial y by partial c, so we're going to have this one here divided by this one here. Okay, so you can see here in this instance here, whenever you divide this out, this sign will cancel with this sign here, and you'll just be left with the x plus b upon c. that's minus x plus b upon c, and whenever you divide out the cosh with the signs, you get this coth function. So that's coth x plus b all upon c. So finally, we're going to equate this one here with the left hand side. So we're going to have our coth x plus b upon c minus x plus b upon c is going to equal, well, the x is going to be the value of a. So it's going to be coth of a plus b upon c minus a plus b all upon c. So there's a wee bit of differentiation in there. If you get stuck or you're unsure, you can always get in contact with me and I can talk you through it. And I'll possibly put the full division here up in the appendix. But it's reasonably straightforward doing the division here of these two equations. So this is the equation that we've seen whenever we looked at the coth function, which was within the graphical calculator. So let's go open that up and we'll have a look at that again. So again, this is the graphical calculator, which you've got the file there for, which is called Catenary 1. So you can open that up if you like and you can have a play about with it. But this is the equation that we have derived here. And you'll note that whenever we head in over to the left hand side, this is just the equation we've got, x plus b upon c minus x plus b upon c. And this is an equality, but what we do is we take this over to this side here, okay, to give us the entire equation, okay. So in effect, that whole thing there would equal 0. Okay, so this would give us equation if I bring it back up. Okay, so this equation here is the analytic derivation. That's how I was able to generate this equation. So let's put the equation on, and again we'll have a look and see what it tells us. So when we put that on, we get this function here, and the position of the x-axis, that is the roots on the x-axis, tell us where the different conjugate points are going to be. So for example, this point here in this graph, say there, is going to have a conjugate point which is over here and up there. And if I was to move this about, so if I move it, say, over down this way here, then we're going to say that if we take the y coordinate here, this point up here in the catenary is going to have a conjugate point at, and we come along here at this point over here. So we'll just line it up with what we've got here. Okay, so again we can just look at our lines. So that's our two lines there, and we can line up our function here, and you can see it's lined up there. So this point here, this x coordinate here for this conjugate point is going to give us the x coordinate for the other conjugate point. So it does work. So I think that's enough for our conjugate points on a catenary. If you're interested in the Introduction to Calculus of Variations on the Charles Fox book, you can always head up to page 49 of that book if you happen to have it, and you'll see that there's another little graphical explanation, which again I've not done here, but I do have on the written notes, so you can also have a look on that for the written notes, and that really shows us that the tangents of the conjugate points on a catenary actually lie on the directrix. So that's all for this video. It's been quite difficult, quite long, but if you have the Fox book, you can go and have a little read over it as well, and if you get any questions, then just get in contact. Thank you for listening. I'll get you on the next video. Goodbye.